being dissolved in the water. So as you can see, the solids being dissolved and you get AQ, but don't forget you got water in there too. Okay, we got to consider that because it can be either oxidized or reduced at the anode or cathode, depending on the potentials. So here they gave you the list of the half reaction and the potentials, okay, like so here. Now, this would be the first solution in the pencil electrolysis lab if we had time to do it. But I really like this lab too because you get basic solution and acidic solution out of the water being oxidized or reduced, so you can see pretty indicator change colors that going on for this particular lab. An electric current is applied to 1 molar of our sodium sulfate solution. All right, so this is an electrolytic cell, tells us that it is not thermodynamically favored. It is unfavorable because we're adding a power source. All right, so looking here, this is probably the hardest part, is figuring out what is being oxidized and what is being reduced. What is being oxidized at the anode, what is being reduced. Looking here, you have to consider that all of these written up here are written in terms of reduction. These are all written in terms of reduction. What we know in solution is the sodium sulfate dissolved into sodium ions, sulfate ions. Those are floating around, soluble salt. The other possible reactant would be liquid water. So you have those 3 possible reactants in there. While we see all of our reductions, we have water as a reactant here and sodium as a reactant there. So we do not need to do anything to those. Those are already correctly written. The other 2, though, it shows water as the product. So this is the one where we would want to flip it, okay? We would want to flip it. So here we would get the 2H2O, flip that over, and this ends up making this negative like so. And then we want the sulfate as the reactant here, so we would want to flip that one. So 2 sulfates going to the other compounds here. That would make this one negative this is for the E-ox in terms of those. Now, looking at these possibilities, oxidation-wise, is water or sulfate, which one's going to be oxidized at the anode based off of these values we just figured? Which one has the more positive oxidation potential? Yes, so the water, that's when we would write out here. This is the one that's going to take place in the reaction. This is the one you would want to write out here. And don't forget, this is a little acidic. So it would change indicator colors because you're producing hydrogen ions. Now, it says write out the balanced reduction half reaction. The balanced reduction half reaction. So out of the 2 that are being reduced here, we have sodium or water. Water or sodium, which one of those is going to be reduced at the cathode? Which one has the more positive reduction potential? This one or this one? Both of them are being reduced. Water again wins. So if you were trying to isolate sodium or sulfate here, this is not a very good reaction to do so. So the water being reduced, plus the 2 electrons, don't forget those, gives you hydrogen gas and some hydroxide. So this one would change indicator colors to a basic or alkaline because you got hydroxide being produced. Now, a couple added things that they mix in with this question right here is which reaction takes place at the anode, the oxidation or the reduction. So that's a straight up knowledge question. So which one takes place at the anode? We know this, always, always. That's going to be anox, red cat, right? So this one has to be oxidation. Always takes place at the anode. Very simple, easy point to get. And then D throws in some thermo with it. Electrolysis reactions have the same sign for delta G. Is the sign positive or negative and justified? So what do we know about electrolytic cells? Are they thermodynamically favored or not? Are they favorable or not? Yes, they are not favored. So that means if they're unfavorable, what's the sign of your delta G? Delta G is always positive for things that are thermodynamically unfavorable. So that's how you would justify it. You would say this is an electrolytic cell using an outside power source. The reaction does not occur without outside intervention, and therefore delta G would be positive. So the sign of delta G is positive because the reaction is non-spontaneous or thermodynamically unfavorable, where the energy in the form of electrical current must be applied for the reaction to occur. I don't know if you need to say in the form of electrical current, but you must say where, energy must be, added in for the reaction to occur. Stoichiometry of electrolysis. This is the fun part. They always ask one of these questions. Apparently they did, I think, on Admin 1, but you're going to be able to work these just in case they show up again. This is a very good calculating the mass of plating. Current you measure in amps or amperes. And an ampere is defined as 1 coulomb per second. So this is how we're going to use it as a conversion factor in our T-chart. So you get a time amount, whether it's minutes, hours, or seconds. You're going to convert the time over to seconds, and then you can use the amp as a conversion factor to get you to coulombs. Because coulombs now, you will use, once you're at coulombs, you use Faraday's constant. And Faraday's constant you could set up as a conversion factor as well, where you have the 96 or 85 coulombs per 1 mole of electrons. So now, once we get to coulombs, we can use Faraday's constant to transfer over. And when we get to moles of electrons, then we just use our balanced reaction. Because the moles of electrons are going to be equivalent to a certain moles of the analyte, and really what we're talking about here is the metal, because that's what we're trying to plate is a metal. Once you can do moles, it'll be something like moles of electrons to moles of whatever metal. And then you can do the moles of the metal to, let me write that on the bottom, it should be on the bottom. Moles of the metal going to the grams of the metal, like so. So it's going to become this big dimensional analysis where we're setting up the fractions, and we're going to be able to calculate. Now, there are 2 ways that they give this to you. Sometimes they give it to you starting with the time and you find the grams of how much is going to be plated. Sometimes they give you the grams or milligrams or something like that, and you have to work backwards to the time that it's going to take in order for it to complete the plating. So it's going to go both directions, and I've given you problems to show you examples of both. So let's go ahead and work some of these. Write out the stoichiometry if you want. I set it up in a big T-chart, so if you're starting with time, you could start with hours. You have to convert the hours to seconds first. Then this is where the amps come in. Okay, this is where the Faraday's constant comes in. And then this is switching over, to the moles of the metal. And then this is going to be the moles of the metal that you want to plate, so forth. The only difference in the bottom chart is, say you start with minutes instead of hours. You just change those to seconds first. You still do the amps here. You still do Faraday's constant, and then you go to the moles of electrons to the moles of the metal to grams of the metal. So either way you want to set it up, just got to set it up so that everything's diagonally canceling along the dimensional analysis, eventually getting to your end result, which is either going to be grams or it's either going to be the time. So you either start with grams and go to time, or you start with time and go to grams. Two different ways of working this, setting this up. So let's go ahead and take some time to do one of these problems. Well, actually there's three, so we're going to do three of them. All right, mass of each of the following, although we're just doing this one here, we're going to look at the hafnium. We're taking hafnium 4 and creating hafnium solid. And we're going to run it for 1 hour at 15 amps. And we want to know how many grams mass, how much is going to be produced. So we're starting with 1 hour. This one's starting with time, so 1 hour. From hours, I can go 2 minutes, or I can go directly to seconds if you remember that it's, 3,600 seconds, 60 times 60, right? So 1 hour equals 3,600 seconds. Now from seconds, I'm going to take those and diagonal down. Now I can go to coulombs. And don't forget, remember, amps equals 1 coulomb per 1 second. So we have 15 amps, so we're going to have 15 coulombs per 1 second here. Now we can go and take the coulombs and diagonal down, and we can go to moles of electrons. So this is 1 mole of electrons equals Faraday's constant. So we're going to use Faraday's constant in here. Now that we've gone to moles of electrons, we can take the moles of electrons, diagonal those down, and go to, so we have 4 moles to 1 mole. So 4 moles of electrons to 1 mole of our hafnium solid. And then 1 mole of HF is going to give us how many grams of HF. So we need to look at our periodic table for that one. And what do we get for hafnium? Let's see here. HF is going to be 178. What does it say? It says 178.49 on the periodic table for AP. 178.49. Now check log everything to make sure it cancels. Hour, seconds, coulombs with coulombs, moles of electrons, moles of the hafnium, and we do end up getting our grams, which is what we want. Then all you have to do is calculate. So 3,600 times 15 times 178.49 divided by the 96,485 divided by the 4, right? So we should end up getting how many grams? Getting 25 grams of HF. And I'm using 2 sig figs because there's 2 here and 2 here. So that's one example. They gave you the half reaction, so you didn't have to figure out the moles of electron, which is nice. Because in this next one, they don't give you the half reaction. They do tell you the time. They do tell you the amps, but they're saying you're going to make chromium metal from molten chromium something oxide here. So I need to figure out what is the charge here for my chromium in my CrO3. Oxygen's -2, so what is going to be the chromium's charge there? Yeah, this has to be a +6. So that means this is going to be 6 moles of electrons. Because if we look at our reaction here, it's going to be the CrO3 plus the 6 electrons. That's going to give me my chromium solid, which is what I'm trying to plate. So we're going to need the 6 moles of electrons here. You had to figure that. That's an extra added step here. So now we still start with our time. But in this case, now I'm just going to do 1 minute equals the 60 seconds and be able to go from there. Then we have seconds to coulombs, and we have for our amps, remember amps, that's going to be our 9.5 coulombs. Come on, why are you not erasing? All right, 9.5 coulombs per 1 second. So that's what we put here, like so. Then we can do Faraday's constant, 96 for 85 coulombs equals 1 mole of electrons. And then we have our 6 moles of electrons. That's what's going to our 1 mole of our chromium solid. And then 1 mole of the chromium solid is going to be 52.0 grams of chromium off the periodic table. So same type of problem, but in this time we had to figure out the moles of electrons based off of the information provided. Check everything to make sure it cancels. Minutes with minutes. Seconds with seconds. Coulombs with coulombs. Moles of electrons. Moles of chromium to moles of chromium. And then we end up with our grams of chromium, which is what we want. So do the math real quick. 35 times 60 times 9.5 times 52 divided by 96,485 divided by 6. And I'm getting a mere small tiny amount of 1.8 grams of the chromium. Not very much chromium from that 35 minutes being produced there. All right, last question, last example. How much time in minutes would it take for 425 milligrams of iodine to be plated from a solution of Ki at a current of 8.4 amps? All right, so we're going to actually work backwards here, starting with the grams to go to the time, milligrams actually. But this one also doesn't tell me the moles of electrons, so I have to figure it out. So I'm making I2, I'm plating the I2, which is a solid, from the Ki, and Ki solution, remember, Ki really is going to break apart into K plus and I minus. What do we care about? We care about this part. The K is just a spectator. So I have I up here. I'm going to need 2 of them. So how many electrons are being transferred in this half reaction? And where do they go? Do they go on the right or the left? Are we being oxidized or reduced here in order to make the I2? Yes, this is going to be oxidized to make the I2. So it needs to lose the 2 electrons to plate the iodine, correct. So we know now that we have 2 moles of electrons. That's what's going to be transferred here. So we can start our chart. Let's do this. 425 milligrams. This one's going to be a long one. So I'm going to start here, and I got to do milligrams, 2 grams. So 1,000 milligrams equals 1 gram. That one's pretty easy to change over. Then now I'm going to take my grams and diagonal them down, and I can go to the moles of the I2. So 1 mole of I2 equals how many grams of I2? Well, I go over to my periodic table, and it says it's like 126.9 for iodine, so 126.9 times 2. And this is going to be 253.80. Now that I'm at moles of I2, I take those, put those down here. Moles of I2. 1 mole of I2 gives me 2 moles of electrons. So 1 mole of I2, 2 moles of electrons. And then I can do moles of electrons down here. 1 mole equals the 96,485 coulombs. Now eventually, coulombs goes down here, seconds going to go up here. So we're going to have to flip our amps. In this case, it's going to be 8.4 coulombs per 1 second to go into our T-chart. So 1 second to 8.4. And then I want minutes, so this is going to be 60 seconds equals 1 minute. Long chart. Milligrams cancel with milligrams. Grams cancel with grams. Moles of I2, moles of I2. It's a good process. Moles of electrons to check and make sure everything works. Coulombs with coulombs and seconds with seconds. And we're left with minutes, which is what we want. So 425 times 2 times 96,485 divided by 1,000 divided by 253.8 and divided by 8.4 and divided by 60. And you should get for your minutes 0.64 minutes as your final answer. So you might see one of these electrolysis calculations where you're doing the stoichiometry for the plating. Like I said, you're basically either going to get starting with the grams or milligrams and going to time, or you're going to get time going to grams. So it's going to be either direction. The likelihood that you'll see this, on the free response will be some kind of form like that. They might give you the half reaction where they already tell you the moles of electrons. If not, you have to figure that out based off the information they provide in the question.